HA2, this is my second video in which we're going to confront how to write quadratic equations given certain initial information about, quadratic situations. So we broke it down into three separate situations last time. We said, well, depending upon the initial information, we're going to have to choose the situation that is most fitting to what we see, with what we're given here. In this video, what I'm going to point out right now is this. We're going to write an equation using a point. So we have some point on our graph, x, y. We need at least one. And then the x-intercepts. And so this is the second situation where it says we're given a point x, y, and the x-intercepts p and q, such that we could write this then in intercept form. What better way to write this than in intercept form if we know some point x, y, and these two intercepts right here, p and q. So let's go ahead and read through this first situation. It says the meteorologist creates a parabola to predict the temperature the day after tomorrow, where x is the number of hours after midnight. We can see that on our graph here. So number of hours after midnight, as it continues to go, we see the temperature is on our y-axis, and it is dropping. And then eventually it reaches a point just after, it looks like, noon here, where it starts to rise again, okay? And I don't want to say, I guess we could say noon. 12 hours after midnight is noon. But the temperature starts to rise again. So using what we know here, we have some temperature, time and temperature data. So at midnight, we say it's 6.3 C, but 6 hours after midnight, it looks like we've dropped down to 0 degrees C. And then it looks like here, I would say it looks like we're going by a scale of threes. So we'd say this would be 15, 18, and 21. Here is this 21 right here, actually. We're given 21 hours after midnight. We're back at 0 C. And we aren't really sure what this data value is right here, which we could use the equation to find, but it looks like it's in the neighborhood of between 2 and 4, like maybe 2.5 or something like that. So let's do this. We want to write the equation of this and then maybe use that to predict, well, when we are now, I guess this would be, if this is 21 here, 24 hours later, what is this temperature right here? If we're going by threes, that would be 24. So let's start with this. Because we know the intercepts, we certainly do know these intercepts. I'm just going to highlight these right here. What we're going to use for our values of p and q, as a matter of fact, are actually the intercept values or the x values. So we'd say that 6 would be one of our intercept values on the x-axis, and 21 is our other intercept value. And then the other thing we want to mention here is this. We know some point on the graph, and we're saying that this is some point x comma y. So we know that our x value here is equal to 0 and our y value is 6.3 degrees Celsius if and only if the x value is equal to 0. But using this information, what we'll do is we'll plug it into our intercept form, which looks like this. We have y equals our a value, which tells us whether it opens up or down. And then we have x minus our first intercept, x minus our second intercept, p and q respectively. So really, just like we did in our last video, what we're going to be doing is plugging in for all the information that we know, that we're certain of. Try to squeeze this stuff in here. And we're going to work backwards really to solve for this unknown a value. And then once we have that, what we can do is we have a, p, and q, and we could go back and rewrite this equation more generally, leaving x and y alone. So let's go ahead and plug in what we know, starting with our x and y pairs. We know that when x is equal to 0, so we'll plug in zeros for our x's here in this expression. We know that when x equals 0, that our output or our y value here is 6.3. So what else do we know? Well, we know one of our intercepts is 6. So we'll put that in right here, and we know the other intercept is 21. So I'm going to have to kind of squeeze that in there. But simplifying this, we will need a calculator to do some of these calculations, but we have a times, now 0 minus 6 is negative 6. And we have 0 minus 21, of course, is negative 21. So maybe we won't need a calculator on this first step. I suppose a negative times a negative is a positive, and 6 20s would be 120, so 6 21s would be 126. So we get 126a. And then just carrying out this division right here, we say divide both sides by 126. This is going to give us the value of a. So getting our calculators out now, we say, okay, let's do this. We say 6.3 divided by 126. We get this rational value here, which is about a nickel. We say it's 0.05. So now here's the idea. Now that we know a, and we also know p and q, what we can do is we could go back and write this equation in intercept form, where our a value here is this number that we're putting out front, this coefficient. And we say that x minus 6 and x minus 21 would fit in here also, because p and q are 6 and 21 respectively. So just to kind of finish this up, not that I need to find this necessarily, but I say, okay, well, 24. When x is equal to 24, approximately what is our value right here? And I had a good guess. It was in the like 2.5, 3 range. If we were to say now, let's plug this in. We get 0.05. We'd have 24 minus 6 and 24 minus 21. Let's go ahead and simplify this. We get 0.05 times 18 times 24 minus 21 is 3. And we'll just use our calculators to carry out this calculation. So we have this 0.05 times 18 equals times 3. So pretty darn good. We'd say it's about, or exactly in this case, according to our model, 2.7 degrees C, which is supported by this graph you see here. So just like in my last video, what I've done here is I've given another example. It's not an application problem, but I certainly have given bits of information here. We say it passes through the point xy, which is 2, 5. We have a data point, and we have the two intercepts here, which are going to be P and Q, -2 and +4 respectively. So I would encourage anybody watching this to kind of pause the video at this point and try to use this intercept form to plug in what you know and work backwards to solve for this unknown A value. But if you want to see the solution, I'm just going to go ahead and start working on it right now. So we say we have our intercept form. So we have our A value, which is always present, and we say x minus P, x minus Q, where these are our intercepts right here. So in this particular instance, we say y equals A, x minus P, x, oops, got a little carried away there, x minus Q. And we'll go ahead and plug in our x and y pair first. We say when x is equal to 2, we get a y value of 5. And we also know that one of our intercepts is -2, so I'm going to write a -2 in here, and I'm going to write a +4 here. So I hope you notice this. When we simplify this expression, or set of expressions this time, looks like we get a, and we get 2 minus a -2, which actually causes this first value to be 4. And then 2 minus a +4 is a -2. So simplifying this further, we get a times a -8. So let's just write a -8a. And we could solve for a here and get -5/8. And if you're interested in a decimal, because I know my eighths, sorry about that, 0.125 is 1/8, so 5 of those is this guy right here. It's negative, okay? So if we were to imagine what this looks like, you know, if I were to say, go sketch what you think you know about this, well, we know that 2, 5 is a point on the graph. Some point. We don't know which point, but we also know that it hits the x-axis at -2, so here's one of our intercepts, and +4 right here. So we'd say that we have this parabola that does indeed open down, if you can kind of imagine. I don't really know where the vertex is, I haven't found it yet, but it opens downward and goes through those points. So now let's go back and write the equation. And again, when you write the equation, we say let's leave x and y general. What we're going to do is we're going to plug in the values of a, in this case -0.625 or 5/8. And we say that we have also the values of our intercept. So we said -2, which actually made this look like a +2. And we say x minus a +4, which makes it look like this. So this would be our equation right here. So one last thing I want to mention is this. Because we have an intercept at -2 and another intercept at 4, we say, well, where would the axis of symmetry be? And we could deduce, we could, figure out that it must be at x equals 1, because what we know about the axis of symmetry is that the AOS has an equation, at least when it's in intercept form, that is the average of the two intercept values here. And in this case, we get 2/2, which is 1. So if we did actually want to find the value of the vertex, we could say it's up here somewhere, and it has an x value of 1. All we would need to do now is go plug that 1 into the function to go find the y value, which I would encourage you to do.